besides going to talks, learn more about the wonderful location. And also the fact that this is the first MCA meeting, to me, is a wonderful opportunity to connect the different parts of the Americas. And coming from Canada, Canadians love Mexico. And often they love coming here in the wintertime, but the summertime is good too. So what I'm going to talk about is a problem that people have been thinking about for a long time. And this is how to understand biological invasions. Biological invasions occur when people typically introduce a new species where it hadn't been found before. And this is often through trade or some other transport mechanism. And they grow and they reproduce and they spread spatially, and they can have a very large impact on the environments they encounter. In fact, after habitat degradation, invasive species are probably the largest impact on species diversity loss. And they cost a lot of money. So one estimate is just in the United States alone, the cost of these invasive species exceeds $100 billion a year. So there's lots of social and economic reasons to look at these. There's lots of biological reasons. As a biologist, an invasion would be like some very large uncontrolled experiment that you try to understand using a dynamical system, and that's my approach. The kinds of questions you might ask are, can an invader establish itself in a new environment? Will the population spread, and if so, at what speed? And what kinds of interactions will it have with other species? I'm going to focus primarily on the second question. And this question really goes back about 80 years. So there's this long and beautiful history of people thinking about biological invasions using mathematical methods. I'm going to focus later in the talk on these two invasion processes that I've picked out a number because they're mathematically very interesting. And I'm just going to mention them very quickly here. The red squirrel is a squirrel which is common to the United Kingdom. And the gray squirrel is much larger. It's from America. And it is out-competing the red squirrel, and there's very reduced range of red squirrels now. And in England, they love their squirrels, and there's been an amazing amount of work trying to figure out how to reverse this invasion process. Another kind of invasion we can think about is for disease, and this is the invasion of West Nile virus in North America. And it's also moved into Central America. And it was probably introduced by a shipment of fruit, like bananas, with mosquitoes that were infected on it in 1999. And then it spread as a wave across North America. And you might try to figure out how it spreads and what controls the rate of spread. Okay, so these are some of the ideas I'm going to talk about. I'm going to go back to some genetic work from the 1930s that goes back to R.A. Fisher and a very famous equation. And I'm going to talk about that. And then I'm going to talk about an associated question, which is, why do invasions sometimes move very, very quickly? Much quicker than we would ever imagine them. And there's some way we can understand this mathematically. And then I'm going to move to some new mathematical work, and this is really interesting in the context of how to analyze spreading speeds. So if you have interactions between species, it's really not clear how to understand things mathematically, and it's rather subtle. And I hope to persuade you of this, and then I'll talk about some applications. Okay, so Fisher was a geneticist, so he was really interested in the spread of a gene into a new environment. And this is a nonlinear partial differential equation with a rate of change of population density. There's a growth term here, and then there's dispersal. And the details are given here. And this function, this growth function here, has the appropriate concave down shape. And in fact, Fisher wasn't interested in invasion of a new species. He was interested in the spread of an advantageous gene within a species. And so he interpreted U as the proportion of the new advantageous gene spreading through the environment. And so you might ask, if you introduce a population or a gene locally and let it grow, okay, and spread, then it's going to move outwards. And how quickly will it move outwards? And this is something that Fisher thought about, and also three rather famous Russian mathematicians, Kolmogorov, Petrovsky, and Piskunov. And they concluded that if you had a certain class of initial data, step function initial data, you'd get a wave that spread at a particular speed here, which is 2 times the square root of r times d. R is the growth rate, d is the diffusion coefficient. Later, Aronson and Weinberger picked up this problem, and they said, well, the initial data that KPP we're thinking about isn't really the right kind. If you introduce a population locally, there's going to be some compact set on which it's introduced, like the one given here, and you're going to get waves spreading in 2 different directions. And you'd like to know asymptotically how quickly this population is going to spread. They call this thing C star. And so the primary mathematical idea they used was to create a solution that would lie below, which is a subsolution, and one that would lie above, and the true density is given in here. And they could calculate how quickly these things would move by creating special ones that they could work out. And then there's a comparison theorem that works for parabolic partial differential equations that says that solutions that are initially ordered will stay ordered for all time. And so if you could sandwich your true solution between these other two, and you can calculate the speeds of these, you can conclude something about the one in the middle. And that's actually the key mathematical concept that comes into play time and time again. It turns out when you look at the history, it's really quite interesting. A chemist named Luther in about 1906 argued that a speed of a spatially distributed chemical reaction should spread at a rate which is proportional to the square root of r times d. We can understand this a little bit if we look at the units. R is a growth rate, d is a diffusion coefficient. If we multiply these two together and take the square root, we're going to get a velocity. So we can understand it with dimensional analysis. And that's what he did. Okay, so what do we mean by a spread rate? Well, the idea is if you're at the point where the population is introduced and you run really quickly or at a speed that it turns out to be bigger than c star, eventually you'll get ahead of the wave and you'll see whatever is out in front, which is this zero solution. If you run a little slower, the wave will pass over you and you'll see whatever is behind the wave, which is this equilibrium point, u is equal to 1. And so if we think about a numerical solution here, a local introduction, and this is space, and we can think about this in terms of these rays. And so if we pick a ray that looks like this, we're going to eventually see 0. But if we pick a ray that looks like that, we're going to be in the region that sees 1. And so that's really what we mean by a spread rate. And so from the previous slide, what Aronson and Weinberger showed quite a long time ago was that that original system, Fisher's equation, had a spread rate given by this 2 times the square root of r times d. One of the key elements here is something called linear determinacy. And this is quite well understood for scalar equations, but isn't really that well understood for systems of equations. So let's look at the system that we're interested in. And this is our growth function, and there's an equilibrium at 1 here, and there's an equilibrium at 0. And we're going to linearize about the 0 equilibrium. And we'd like to replace the nonlinear model with a linear model because we can solve linear models. And often we can't solve nonlinear models. So we say the spread rate is linearly determined if the spread rate for the nonlinear system is the same as for the linearized system. And if this is the case, then we're happy because we can calculate the spread rate for a linear system. And it's true for Fisher's equation. It's not true for many other equations where f has a different shape. Okay, so this is the shape associated with Fisher's equation. And so f lies below its linearization at the origin. Another situation where it has a different shape, this would be appropriate for something more like combustion, or if you have an Ali effect, which is low growth rates at low densities, then it's no longer linearly determined. And so this is a sufficient condition for linear determinacy for a scalar system. And this was investigated in the 70s. We'll come back to these ideas in some of the newer work. Okay, so when I was a postdoc, I worked in an ecology lab, and people were getting really excited about these formulas because they thought, well, there's these two parameters, R and D, and we can go and measure those for potential invaders. R is the growth rate, D is the diffusion coefficient. You can measure these from experiments. You've got a very simple compact formula, 2 times the square root of R times D, and then you can compare historical spread rates for lots of different invasive species to what the theory would say, and then try to make predictions about new invaders. And this is some of the species, including the Black Death in medieval Europe. People have gone back and recalculated how quickly people move from city to city and so forth. So it looks good, but there are some outliers. And one of the outliers is the spread of vegetation after the last ice age. It moved extremely quickly as the ice sheets retreated, much more quickly than we would ever imagine based on these kinds of models. Now, this has an important context nowadays when we look at the impacts of climate change on vegetation and whether vegetation can keep up with the isoclines of temperature. There's another case here of the cereal leaf beetle, which was an insect pest. And when you read the paper, when they try to apply the model, what they said is, well, we think what's going on is that this beetle, it diffuses locally and then it gets picked up by wind currents and then moves along and then it drops a long way away. And this isn't really diffusion, okay? This is the problem. You might be measuring things on a local scale, but then there's these long distance movements that are facilitated by wind currents that will drive the invasion at a much accelerated rate. And so this is really what seems to be driving a lot of the vegetation response historically to climate change. Indeed, Reed was a natural historian, and in the late 1800s, he said the oak, to gain its present most northerly position in North Britain, after being driven out by the cold, probably had to travel fully 600 miles, and this without the aid. External aid would take something like 1 million years. Well, he didn't know what Fisher knew, but he had this idea of trying to understand why vegetation could spread so quickly in response to new habitat opening up with the retreating ice sheets. So this question of Reed was picked up using Fisher's analysis and saying if we know the speed that it moved, and we know the growth rate for trees, how far would these propagules or acorns have to move on average to explain the spread that was observed? And it was, the result was an average of 830 meters. So we know that acorns fall close to the tree. They don't go so far away. And so this was coined Reed's paradox. So how do we understand this? Well, we need a model that includes long distance dispersal. The possibility that things can move locally, but they can also move long distances. This is essentially non-diffusive movement. And there's a number of different possibilities. Often it's useful to use discrete time and continuous space. So n is an index for the time, typically the year, and this is a nonlinear operator. F is a map now, a discrete time map, and this would be equivalent to logistic growth. So if you have a population here, the next year it would be there, and you can cobweb this as you might for a scalar nonlinear difference equation. But now, if you're produced at location y, you can disperse to location x according to a probability density function that spares things out. And now this can take any number of forms, and you could put in fatter tails to describe this long distance dispersal. So this is a more flexible class of models. And it turns out that there's a little story behind this. I started with a colleague, Mark Cott, and Pauline van der Driesche looking at this model in the 1990s. And we came up with some interesting, what we thought were interesting mathematical results. And we sent the paper to review, and Hans Weinberger was one of the reviewers, and he said, it's very nice work. I'm glad you're popularizing my results from 14 years earlier, where he sort of already had the theorem worked out, and we weren't aware of it. So the idea here is, if you lie below, if f lies below its linearization, and then k meets a certain condition, and that is that it has a moment generating function, then you can have the speed as being linearly determined. So you can then calculate the spreading speed. Okay, so if you have a moment generating function, it means that the tails of this dispersal function have to drop off sufficiently quickly. Okay, if they have fat tails that don't drop off exponentially, this condition won't be met. Okay, so and the proof is very, very similar to the earlier work. Okay, you need to create a sub-solution, okay, and a super solution, and watch how quickly each of those spread. But it's more complicated because you're doing this in discrete time, and it's not always clear how to create these things. But there's a comparison theorem for these kinds of integral difference equations, just like there are for parabolic partial differential equations. And so that's what you need to finish the work. Now, it's rather interesting, though, if you actually look at these spreading speeds or spread rates, how sensitive they are to the dispersal function, that k function. And here we took some trap data for insects that is fairly famous from genetically marked Drosophila, and fitted different functions. This is a Gaussian, this is some other function. This is something that looks like e to the minus square root of x. This is an exponential function. And we could talk about calculating the spreading speeds, or we can just simulate it. And here, in this one, and this one, and this one, the moment generating function exists, okay? In this one here, there is no moment generating function because we have a like e to the minus square root of x, okay? So it's not exponentially bounded. So in these cases, we see these waves of spread, okay? And this one, the wave is just moving faster and getting more shallow all the time. Okay, so there's no spreading speed that exists here. Okay, but rather interestingly, it might be hard to see from the back, but this distance here is 1 kilometer, that's 3 kilometers, that's 2 kilometers. So depending on exactly how you fit these functions, you're going to get very different spread rates. And it all lies in exactly how well it fits the tail here. And so this is a lesson that we can learn about the biology. If we don't measure these long distance dispersal events very well, then we're going to get the response of vegetation to climate change wrong. And this was picked up by a number of biologists, including Jim Clark, and used to look at how, say, how trees migrate. Okay. Okay, so that talks about one species, but how about if you have interacting species? A number of things can happen. I'm going to talk a little bit about the theory to start, and then I'm going to move to some examples. And so the idea is that when a species comes into a new environment, it might compete with other species, it might use them as a resource. Okay, there's kinds of interactions that happen, and they could be crucial in determining how quickly a population will spread. And so if we think about higher dimensions, so now we have two or more species interacting, it turns out that if things kind of look like a scalar model in some sense, then they work nicely. Okay, so what do I mean by that? If you have a cooperative system where maybe species 1 helps species 2 and species 2 helps species 1, then the dynamics turn out to be similar in some sense to a scalar system in terms of the flow. And that situation can be understood using these ideas of comparison theorems and constructions of super and subsolutions. And it's possible to sometimes go back and forth from a partial differential equation to a discrete time model there. And I spent a bunch of time actually working with Hans Weinberger and a postdoc, Bing-Tuan Li, in the first part of the 2000s, developing the theory for this in a series of papers. And it's been developed by many others also. But the kinds of questions you might ask are, does a spreading speed exist? Maybe there isn't this constant speed that's found as time goes to infinity. Maybe things are moving faster and faster over time. There's no guarantee that such a speed exists. It could be that one component spreads at one speed and another component spreads at another speed. Okay, we don't have that when we have a scalar system, but when we have interacting species, the components could spread at different speeds. And we'd like to be able to linearize this problem and use a linear theory because that would be useful. But when can we do that? We need to have some kind of equivalent condition to that function line below its linearization. So how would we understand that? And then we'd want to interpret these conditions biologically. Yeah, so I think what I'll do is I have some further mathematical details on this, which I may come back to in the questions, and I'll keep going with the general theme of the talk. And I won't go through those further details right now, but feel free to ask me, and I'd love to show them to you. Okay. So let's look at the gray squirrel spreading into the red squirrel. And this is a very simple equation with competition and diffusion. This is the gray squirrel, the aggressive American gray squirrel, which is actually quite larger. And then this is the red squirrel, okay, which is sort of being pushed back. And they move at slightly different rates. There's a competition term here, so these are like logistic growth, but now there's this cross term that describes the competitive interactions. And if A1 is less than 1 and A2 is bigger than 1, then the impact of the gray on the red is more than the red on the gray, which is sort of what we want. Okay, so that looks like a pretty simple system. It's a very natural extension of Fisher's equation. And you might say, well, if you're interested in looking at how quickly this spreads into the gray, into the red, you just sort of linearize around the leading edge here if you thought that linearization would work, where V is close to 1 and U is close to 0, and then you get a linear equation, and you'd analyze that. Well, that would be nice, okay? So V is close to 0, V is close to 1, U is close to 0. If we plug that in there, we get this equation here. Okay, so, oh, that's nice. That's very much like the linear system we've seen before, where now the R is replaced by R1 times 1 minus A. So we can use that theory to predict a spread rate given by Fisher's equation. Well, that doesn't work. Okay, it actually has appeared in math biology textbooks, but that approach doesn't work here. So somehow, at least for certain parameter regimes, this linearization idea just doesn't work even for very simple problems. And so this was initially, Yuzo Hosono, a Japanese math biologist, noticed this by doing some numerical calculations. And we wanted to try to understand what was going on. So it's sort of interesting, this formula doesn't even involve D2, or it's only involving the parameters associated with, oops, if I go back here, there's no D2 when we linearize this equation, and we just have this. So we thought this should be invariant with respect to the diffusion for the red squirrel, and in fact it's not. Okay, so as that diffusion rate goes up, the linear prediction is violated at some point. Okay, so sometimes it works, sometimes it doesn't work. So that's sort of an interesting setup. Why would that be the case? And how do we understand it? Okay, so we can think about this as a competitive system, but we can turn it into a cooperative system by changing the variables, okay? So if one competes with the other, say U competes with V, then if we change Q into 1 minus V and say P is equal to U, then P and Q help each other, okay? And then we can have a cooperative recursion, and this will be an order-preserving operator, and we can use some of the methods I talked about. And in this case, you can find a sufficient condition for the linearization to give you the right speed. And there's an inequality here that involves all the relevant coefficients, including the diffusion rate for the red squirrel. And notice if D2 gets larger than 2 times D1, this number becomes negative, and so this inequality can never be satisfied. But if D2 is small, then it could be. And so that's sort of what we actually just saw with the numerics earlier. Here, we sort of lose this linear predictability around the point where D2 is equal to 2. Okay. So it turns out that another way to do this is to try to understand it intuitively is using singular perturbation theory. So in a particular limit where some of the parameters either become very small or very large, you can approximate the two-equation system as a one-equation system using singular perturbation theory. This is a limit where D2 is equal to 0, but R2 is large, okay? So that won't be satisfied here either, okay? And you can project the dynamics onto a scalar partial differential equation where the growth function f looks like this. Okay, well that shape of a growth function is very much like the kind that we've got right here, where we know that this is not linearly determined. And so somehow this competitive dynamics is causing, under certain parameter regimes, things to look like they have a growth that doesn't lie below its linearization everywhere. Ecologists refer to that as an alley effect. Okay, so that's an explanation. How about spread of West Nile virus? This is another application where we can use some of these ideas. Shifting gears a little bit. This was a picture I showed you of the spread where the colors show how far it went each year. Well, here, if you're coming up with a reasonable model, it can be quite complicated, okay? So these are mosquitoes and they're interacting with birds, and this really doesn't involve people at all, even though we think about West Nile virus in the context of people. There's this magnification cycle where a mosquito bites an infected bird, the mosquito becomes infected, and then it bites an uninfected bird later, and that next bird becomes infected, returns the favor, okay? And so there's a number of models. This is 4 components for mosquitoes and 3 for birds, okay? There's an interaction term here that involves the cross-infection, okay? These are susceptible mosquitoes meeting infected birds, okay? In the other direction, we have infected mosquitoes meeting susceptible birds, okay? In each of these cases, it causes a change from susceptible to exposed or infected. There's a normalization factor here, which is the number of birds, which is appropriate for these kinds of diseases that are vector-borne, vector being the mosquito, not something in RN. And mosquitoes diffuse a little bit and birds a lot more. Okay, so this is just a very simple system. More complicated ones have been proposed, but initially it's rather daunting trying to look at the spread rate here because you have 7 components. So what kind of thing can you do here? Well, one approach is one can take is to make assumptions that you know are wrong. Okay, and use them to get something that you can understand, and then to work backwards and to find out the impact of those incorrect assumptions. Okay, so that's what we do here. Okay, so we're assuming that mosquitoes move quickly through an exposed class, and The birds don't die from the West Nile virus, whereas some of them do, and so on. And also we assume that birds move quickly through a removed class and become susceptible again. And so if we do that, then we can find this invariant manifold and on this manifold, we can just look at the dynamics of the disease, the dynamics of the bird infections and the mosquito infections. And there we have a cooperative system, because bird infections help mosquito infections, and mosquito infections help bird infections. Okay, so suddenly we're in an area where we have some understanding of what's going on mathematically, and we can look at the spreading speed for this simplified system. And if we simulate both of these systems at the same time, and we just keep track of infected birds, underneath is the solution to the full 7-equation system. This is to the 2-equation system. And over here, you can see a couple of things. They're both spreading at about the same speed, okay, for these estimates of the parameters, and one solution lies below another. So it turns out we can use a comparison theorem again. Okay, and the way we use the comparison theorem again is to deduce the sign of the terms that we're essentially throwing away by making these assumptions. Okay, and then if we know the sign of those terms, then we can basically prove that this system, simplified system here, will spread faster than the full system. So it'll be an overestimate. So we get an estimate, but we know what side of the true reality it'll be on. Okay, and that's sort of what this says. So we have this manifold that involves infected mosquitoes and birds. And on this manifold, we have a cooperative system, okay, that lies below its linearization at the leading edge of the wave. We can get a unique spreading speed for the operator, and then use a comparison method to compare the full system to the more simple system. And it turns out then, of course, you might ask, how well does this model do in predicting the spreading speed for West Nile virus? And so we try to independently estimate the parameters for the model. And you can see about how far it's moved for these estimates, which is about 800 kilometers in 300 days. And the true spreading speed was around 1,000 kilometers a year as it moved into North America and spread across North America. Now, so we felt initially pretty happy about that, but it turns out, as with any biological system, once you think you've solved the problem, you realize you haven't solved the problem. And here, the key dynamics are bird migrations, where some of the vectors, some of the birds, the hosts, actually migrate seasonally to Mexico and other places, and then come back. Okay, so there's a much more complicated bird movement model that needs to be included. Okay, and this has been done, but I'm not talking about it today. Okay, so how do we understand this? Well, linear predictability allows you to calculate the spread rate for a nonlinear model based on a calculation for a linear model. But this is well understood in one dimension, but in higher dimensions it's really not well understood. And so when it applies is subtle, and it's been subject of much mathematical research. This has remained an area of interest, partly because people in math biology often come up with these spatial models that involve growth and movement, and they're interested in how quickly populations spread, whether it's invasive species or something to do with a cancer tumor growth. And usually they do whatever they know how to do, which is to linearize, calculate the spreading speed, and then compare to numerics and say, well, this is what our prediction is, this is what the numerics say, it looks like it's the same. But at least in the case for a very simple model with squirrel competition, this had been done for many years until someone picked the right parameter regime and found that it didn't work. And so we need some deeper mathematical analysis. The other thing is that if you can't kind of somehow massage the system into something that has a comparison theorem, it's very difficult to analyze the spreading speed. And even very simple models, things that involve, say, a predator and a prey, then there's no way you can transform your variables, okay, to make it a cooperative system, because you have this asymmetric interaction between the two species. And so this is a problem people are working on right now. And so the idea is to try to make some kind of analysis where in part of the, say, predator-prey space, things look like they're essentially like a cooperative system, even if there's something else happening elsewhere at different densities. Okay, so somehow to use these ideas of cooperativity, not for all of the values that the variables can attain, but only locally. Okay, so this turns out to be technically a big challenge, but there has been some recent work on this. And the other interesting point here is that rare long-distance dispersal events drive invasion speeds at orders of magnitude faster than Fisher and people had earlier predicted. Intuitively, this makes sense once you explain it, but it had remained a paradox for a long time. Furthermore, a large class of models give these accelerating waves that never actually attain an asymptotic speed, but just go faster and faster and faster. And I hinted at that with the numerical simulations. Remember, there was this condition that this moment generating function had to exist. Okay, so the tails had to drop off fast enough for the theorem to apply. Well, if the moment generating function doesn't exist, you can then do some other kinds of asymptotic analysis on the spreading speed and calculate how quickly it accelerates. Okay, and this is really probably what's happening with responsive vegetation to climate change, where you see a very rapid shift in vegetation right behind the retreating ice sheets. Just some very rare long-distance dispersal events that may be driving the process. And you might say, well, how far do things have to move? Well, if you're looking at things over thousands of years, all you need is several really, really big storms that maybe pick up cows and pickup trucks and move them to the next state. And if they're also picking up beech nuts or acorns, that could be all you need, right? So if you wait long enough, somehow, these are the things that are going to dominate, and these aren't the things we measure. So, so this is a little depressing from a scientific perspective, because the mathematics has kind of shown us that the things that really matter are the things that we can't measure as easily. Yeah, so I think this point is something we've already talked about. Okay, so it turns out there's been this sort of explosion in analysis of these kinds of systems over the last decade to all these different areas. I talked about the non-cooperative systems and spread in epidemics. Henri Beresticki, and there's a big group in France that have looked at what happens if you have spatially and temporally varying environments, time delay, stage structure. One thing I've worked on quite a bit recently is looking at these same questions in rivers where there's a very strong flow, unidirectional flow, as things get washed down rivers, and you can use these same ideas there. Okay, so thank you very much.
Are there any questions?
Great talk.
Thank you.
You said that there's some.
Yeah, it's good.
Yes, in Brazil, actually, something physical model something by Roberto Franklin recently for the Amazon, because they had a problem about the use of the Amazon space, so it's a function of the space. And so they see that according to how which space was available with the competition of two species of trees, one would dominate over the other and they could coexist. So this was very...
That's very interesting.
I'm wondering if, well, And the second
Yeah, I think I've seen the paper, but
Roberto Crack.
yeah, it's very interesting. Yeah.
And the other thing is about the epidemics. We do dengue, and so in order not to have all this, but I understand your approach. You try to see the cultivation between the two species.
Mm-hmm.
But for the humans, for example, there are so many more mosquitoes, the humans. So to simplify the model, we put the mosquito inside the parameter. So the infection parameter is actually kind of competitive to take advantage of this. And so maybe I would like to talk with your model.
I'd love to. Yeah. Thank you for telling me about that.
Any other questions?
Hi, thanks, Mark.
Thank you.
I have a quick question. From a biological point of view, what do you gain or lose when you consider only discrete time? What are the advantages and what are the shortcomings
Sure.
when you consider those models?
Yeah, so that's a really good question. So you can formulate, say, integral differential equations that have long distance dispersal and continuous time. So there's no, I went to discrete time, but I could have, talked about things in continuous time, even with the long distance dispersal, but I didn't. And my own bias is to use discrete time because almost all the questions I've been interested in happen on a seasonal basis. And so you're looking at things from year to year where there may be a dispersal stage and then a growth stage. And so it's very natural to look at things in discrete time. It turns out that one can sort of map back and forth mathematically. So if you have a system of PDEs, we found when we did our analysis, it was easiest to take, say, the cooperative PDE system, map it to a discrete time system, and think of it as a discrete time map on function spaces, and analyze it, okay, create these super and sub-solutions and so forth, and then map back later to the PDE. The early work by Aronson and Weinberger did all this in the phase plane because they had a scalar system and they were looking at, in sort of, they could do their analysis in the phase plane. When you get in higher dimensions, more species, it's very difficult to analyze the PDEs directly. It's much easier to map it to a dynamical system that coincides with the solutions to the PDEs on regular time intervals and then map back and forth. So there's sort of there's both mathematical and biological aspects to that question.
Any other question? In the back?
I have a very nice question. Why do you assume your diffusion rate is diagonal? I can imagine in some cases it is, but I can imagine gray squirrels chasing red squirrels. Maybe it's not.
Yeah, great question. Yeah, so there has been some work on that, but not very much. Most of the classic work has thought about the interaction on the growth, but not on the dispersal. But certainly there has been a little bit of work on that. I haven't done any, and so it could be that they're affecting each other's movement patterns. And, it's a lot more difficult. I guess it all depends on the sort of the eigenvalues associated with that matrix of the diffusion operator. So very nice. Yeah.
So, thanks, Mark. The thing that seems to be most difficult to model is the F, your growth rate function. So what happens if and for certain growth rate functions you claim, or the theorem showed that linearization works.
Right.
And has anybody looked at varying the growth rate functions so that linearization breaks down? And this is a bifurcation question where you might get some insight into how the nonlinearities are really affecting the end result.
Yeah. We've done a little bit of it in multi-dimensions, but the work that's in somehow nicest is for scalar systems because it's easiest to understand. And so there, Hadler and Rote, in the 70s, they looked at sort of continuously deforming that, that F function from something that lay below its linearization to something that no longer did. And so the terminology they used to describe what would happen was going from a pulled wave to a pushed wave. So a pulled wave really spreads because of the individuals at the very leading edge of the wave that are growing very, very quickly, quicker per individual than anywhere else, and then they're diffusing, and so this is pulling the wave along. With a pushed wave, basically the growth rates at the leading edge of the wave per capita are quite low, but they're higher further back. And so the individuals further back are growing, and then they're spilling over, and they're kind of filling in the deficit at the leading edge of the wave. And there, the entire shape of the growth function matters. Okay, so you can't get away with a very simple linearization. You have to know the exact shape of the function. And in certain circumstances, you can exactly calculate that speed. And that's what sort of what Hadler and Rote did. But the devil's in the details. And I don't know of a very nice general theory. Yeah.
We have time for one last question. Nobody? So, yeah.
So I was just wondering, your assumption is that the biological systems is a field, right? So when you basically make a computing assumption that it's species of these individuals.
Yeah.
So for the examples you talk about, especially where you saw deviations, to which extent does it matter that it underlying to be discrete dynamics of individuals?
Yeah. Boy, that's an area that's been really kind of rich for research. So there's a number of things that can happen. Well, if you have a population that where individuals don't interact, so it's a completely linear system, then the fact that you're dealing with individuals rather than densities doesn't make a big difference. So you can, there's some theorems that connect the two spreading speeds. If you have nonlinear interactions, then what can happen when you follow individuals is that the model isn't exactly right, okay, that people have been writing down because it's a mean field model. Okay, so it assumes that the probability of two individuals interacting is the product of their densities. Whereas you would really have spatial correlations that arise between individuals as they grow and disperse. And so in that situation, it's possible to show that the mean field model overestimates the spreading speed. Okay, so that by including, at least for a scalar system, that by including positive correlations, okay, you actually can get density-dependent effects at the very leading edge of the wave, where you wouldn't expect them from the mean field model. And so it's a rich area of research, but it's fairly difficult. And I've dabbled in it a little bit, and I know other people have done more significant work in that.
Mark, will be around this week, so please.
Thank you.